Welcome to this practice session for signals and systems. This video is prepared for helping students in practicing numerical examples. In this video, we will be working on numerical examples related to basic operations on signals. For one-dimensional signal, there are two parameters associated. One is independent variable, which is either continuous time or discrete time. Another one is amplitude, which is the dependent variable. As you can see, independent variable is marked on horizontal axis. Dependent variable is marked on vertical axis. The operations on signals are classified into two based on these two parameters. One is operations on dependent variable, another is operation on independent variable. Considering the operations on dependent variable, there are several operations defined. First one is amplitude scaling. Second one is addition. Third one, multiplication. Differentiation is defined. Integration is also a defined operation. In the case of independent variable operations, we have time scaling, time reversal, and time shifting. Now let us go to problems related to all these operations. Let us go to the first problem. A signal is given x of t is equal to 1 when t lies between -1 to +1. It is 0 otherwise. The graph of the signal will be like this. The spread of the signal is between -1 to +1. Amplitude is 1. When t greater than +1, it is 0. When t less than -1, the signal is 0. The question is to plot a compressed version and an elongated version of this signal with a scaling factor, say A. We can consider two cases. Case 1, when A is greater than 1. The definition of the signal will be xat is equal to 1 when at lies between -1 to +1. It is 0 otherwise. To compress or elongate a function, we have to multiply the independent variable t by the scaling factor a. As we have multiplied here also we should multiply. Now let us rewrite this definition such as t lies between -1 by a to +1 by a. These two definitions are equivalent. When at lies between -1 to +1, t will be lying between -1 by a to +1 by a. So now the definition is x of at is equal to 1 between these limits. It is 0 otherwise. Now let us plot this signal as per the definition. We can see that the amplitude is 1 between -1 by a to +1 by a. And also it should be noted that there is no change in the amplitude. Here the signal is x of at instead of x of t. Now if the value of a is equal to 2, y of t is equal to x of 2t. Let us plot this and compare with x of t. We can see that the limits minus 1 by a to plus 1 by a is now minus 1 by 2 to plus 1 by 2. Amplitude remains the same. This is x of 2t. And if you compare with x of t, which was lying between minus 1 to plus 1 with the same amplitude, we can see that there has been a compression of this signal occurred. So this is the time scaled version, a compressed version of the signal x of t. Now let us go to the second case where the scaling factor a is less than 1. Let us assume a is equal to 1 by 2. The definition of a time scaled signal is the same. X of at is equal to 1 when at lies between minus 1 to plus 1. It is 0 otherwise. Now let us substitute for a by 1 by 2. So it becomes x of 1 by 2 t is equal to 1 when t by 2 lies between minus 1 to plus 1. If you modify this definition, t lies between minus 2 to 2, x of t by 2 is equal to 1. It is 0 otherwise. Let us plot the signal now. We can see that the limits have expanded to minus 2 to plus 2. Throughout this interval, the amplitude is 1. Now if we compare this with the original signal x of t, which was lying between minus 1 and plus 1, we can see that time expansion on both sides has happened to the signal. So this is the elongated or expanded version of the signal x of t. In general, we can understand the expansion of the signal in this way. The signal is expanded by a scaling factor a, which is less than 1. Then the signal should be marked as x of 1 by at, and the limits extends to minus a to plus a. Amplitude remains the same. Similarly, for compression, the general form of the signal will be x of at, the limits change to minus 1 by a to plus 1 by a, with the amplitude remaining the same. This is x of at, this is x of t by a. Having understood this, let us go to the next problem. Given a triangular signal with amplitude equal to 1, which spans between minus 1 to plus 1. Question is to draw the compressed and elongated versions of the signal with the scaling factor a is equal to 2. We can think in terms of these general forms, how the compressed and elongated forms of this particular signal. Straight away we can draw. The compressed version has got the limits equal to minus 1 by 2 to plus 1 by 2. Amplitude remains the same. This signal is x of 2t. This is in comparison with this general form x of at minus 1 by a to plus 1 by a. Now regarding the expanded version, we can have x of t by 2. The limits are expanded to minus 2 to plus 2 from minus 1 to plus 1. Amplitude remains the same. Now it is very easy to draw the compression and expansion of any given signal. Let us go to problem number 3. A discrete time signal x of n is given as shown in the figure. Find out y of n is equal to x of 2n. This is a question related to time scaling. The scaling factor is 2. Now we need to substitute for n with different values, say 0, 1, 2, 3, minus 1, minus 2, minus 3, etc. in order to find out different values of y of n. Corresponding indexes of x we have to find out. Then we should choose the values from this graph to find out what is the value of y of n. When n is equal to 0, this equation becomes y of 0 is equal to x of 2 into 0, that is equal to x of 0. What is the value of x of 0 from the graph? It is equal to 0. So y of 0 is 0. Now when n equal to 1, y of 1 is equal to x of 2 into 1, that is x of 2. The value of x of 2 from the graph of x of n is 3. That means y of 1 is equal to 3. Similarly, y of 2 is equal to x of 2 into 2, that is x of 4. From the graph of x of n, x of 4 is equal to 1, that is y of 2 is equal to 1. Now y of 0 is equal to x of 0, 0. Y of 1 is equal to x of 2, that is 3. Y of 2 is equal to x of 4, that is equal to 1. If we substitute further values of n, say y of 3, on the right hand side it is x of 2 into 3, that is x of 6. From the graph, x of 6 is equal to 0. For any further values of plus n, positive values of n, the amplitude will be always 0. That means y of 4, y of 5, etc. will be 0. So we need not calculate further. Let us try to find out the negative index terms for the signal y. And n is equal to minus 1, y of minus 1 is equal to x of 2 into minus 1, that is x of minus 2. The value of x of minus 2 is 3 here. So y of minus 1 is equal to 3. Y of minus 2 is equal to x of 2 into minus 2, that is x of minus 4. As per the diagram, x of minus 4 is equal to 1. So y of minus 2 is equal to 1. Y of minus 3 is equal to x of 2 into minus 3, that is x of minus 6. And it is evident from the graph that x of minus 6 is 0. For any further values for negative n, it is 0. We need not calculate further. With the values which we have obtained now, let us plot the signal y of n. Y of 0 is equal to 0, y of 1 is equal to 3, y of minus 1 also equal to 3, y of 2 and y of minus 2 is equal to plus 1. All the further values are 0 on both sides. So this is the time scaled version of x of n, such that y of n is equal to x of 2n. So we can see that here x of n had many samples. From that, certain samples only are included in y of n because of this time scale. Is this a compressed version or elongated version? We already know that when the scaling factor a is greater than 1, we get a compressed version. Now let us find out the expanded version of same signal x of n. Question is, find out y of n equal to x of n by 2. We can see that the scaling factor here is 1 by 2 which is less than 1. So y of n has to be the expanded version of x of n. Let us substitute for n. N equal to 0 makes y of 0 is equal to x of 0 by 2, that is x of 0 itself. The value of x of 0 is 0. That makes y of 0 equal to 0. When n equal to 1, y of 1 is equal to x of 1 by 2 into 1, which is equal to x of 1 by 2. This 1 by 2 index is a non-integer index, which is not allowed in the case of a discrete time signal. N can take up only integer values. So we equate x of 1 by 2 to 0. That makes y of 1 equal to 0. When n equal to 2, y of 2 is equal to x of 1 by 2 into 2 equal to x of 2 by 2 equal to x of 1. X of 1 value is 4. That makes y of 2 is equal to 4. When n is equal to 3, y of 3 equal to x of 3 by 2, which is again a non-integer index. We equate y of 3 to 0. When n equal to 4, y of 4 is equal to x of 4 by 2, which is equal to x of 2. The value of x of 2 from the graph is 3. That makes y of 4 equal to 3. When n is equal to 5, y of 5 is equal to x of 5 by 2, which is a non-integer index. We equate that to 0. y5 equal to 0. When n is equal to 6, it is equal to x of 6 by 2, x of 3. The value of x of 3 from the graph is 2. N equal to 7 equal to x of 7 by 2, a non-integer index. So y of 7 is equal to 0. N equal to 8 is equal to x of 8 by 2, which is equal to x of 4. The value of x of 4 is 1 from the graph. Any further values of y will be 0 because in x of n, all the further values are zeros. Similarly, we can substitute for the negative values of n also. After calculating all the values of y of n, we can plot the graph of y of n as follows. We can see that at 0, value of y of 0 equal to 0. At 1, it is equal to 0. At 2, it is 4, 3, 0, 4, 3, 0, 2, 0, 1. We can see that the signal has expanded to n equal to 8. Whereas in the case of x of n, it was defined only till plus 4. Similarly, on the negative index side, it has expanded to minus 8. In the case of x of n, only minus 4. Up to minus 4 it was defined. After that it was 0. So y of n is an expanded version of x of n. In the fourth problem, a signal x of t is given as shown in the figure. We can see that x of t starts from equal to 0. This is a continuous time signal. The question is, plot the delayed and advanced versions of x of t. That means we have to do time shifting. Let the amount of delay or amount of advancement equal to 2. That means we can have x of t minus 2 and x of t plus 2. Let us draw the delayed version first. Instead of starting from 0, the signal is starting from equal to 2 now. That means it is delayed for 2 seconds. Similarly, advanced version will be starting 2 units before the actual start of x of t. That means x of t is starting from 0. X of t plus 2 should be starting from here. Let us draw x of t plus 2. This is the advanced version. We can see that if it is a delayed version or advanced version, the shape of the signal is remaining the same, just as in case of x of t. Having understood this example, now let us take another signal, a unit step signal. Let us delay or advance the signal by an amount of say 3 seconds. We have to find out u of t minus 3 and u of t plus 3. The delayed version will be like this. We can see that instead of starting from 0, it is starting from 3. It is u of t minus 3. The signal has delayed for 3 seconds. The advanced version will be starting from equal to minus 3. So that instead of starting from 0, it has started 3 seconds before. The graph will be like this. U of t plus 3 starts from minus 3. The amplitude and the shape of the signal remains the same, whether it is an advanced version or a delayed version. There is no change. So what we should remember is that a delayed version, the shift is towards the right side. An advanced version, the shift is towards left side. In the next problem, let us consider a discrete time unit step signal, u of n. We need to plot u of n minus 2 and u of n plus 2. U of n minus 2 is the delayed version. The sample which was placed at 0 is placed at 2 now. If you substitute n equal to 2 here, this will become u of 0. That means u of 0 here, the value of u of n at n equal to 0, which is placed at this point. The subsequent samples are placed accordingly. It proceeds till n equal to infinity. U of n plus 2 will be, the graph will be like this. The sample which was positioned at n equal to 0 is positioned at n equal to minus 2 now. And the signal proceeds towards positive infinity. At n equal to 1, we can have a sample, n equal to 2, we can have a sample, and so on. Now we have understood the operations time shifting and time scaling, both in continuous and discrete case. Now let us see the last operation which we have learned, that is time reversal. Consider a signal x of t as shown in the figure. Draw the time reversed version of x of t, that is x of minus t. The graph of the signal will be like this. You can see that x of t and x of minus t are just reflections about the vertical axis. If we want to do time shifting of this reflected signal, that means if we want to plot x of minus t minus 2 and x of minus t plus 2, this operation will be slightly different from what we have understood so far. First of all, let us see the graphs for x of minus t minus 2 and x of minus t plus 2. These graphs are not according to our understanding we developed so far. So far what we learned is if it is -2 here, it is towards the right side. Here you can see that this is -2, it is towards the left side. Similarly, here +2, it is towards the left side. Here it is +2, it is towards the right side. The sense of the sign has reversed. That is because the sign associated with the independent variable is also reversed. The independent variable is positive, +n or +t. The shift, if it is a positive shift, it is towards the right side. If it is a negative shift, it is towards left side. If the independent variable is -t or -n, positive shift means towards the left side. Negative shift means towards the right side. As the sign of time reverses, the direction in which the shift or advancement happens also reverses. It may take some time and practice for you to understand this point. Now let us consider few more examples where multiple operations on signals are involved. Plot u of -t plus 1. As you can see, there is a reflection operation and a shifting operation. U of t is the basic signal upon which we should apply these two operations. Let us shift u of t by 1 unit. U of t plus 1 will be starting 1 unit ahead than the actual start. This is the advanced version. Now reflect this u of t plus 1 signal to get u of -t plus 1. This is the mirror image of the signal u of t plus 1 about vertical axis. So this last graph shows u of -t plus 1. Now let us reverse the order of this operation and see what happens. Consider u of t again. Reflect it first to get u of -t. Shift the signal by 1 unit. We should have u of -t plus 1. The shift should happen towards the right side because the independent variable has got a negative sign now. Here u of t plus 1, the shift was happening towards left side. Here as the independent variable is negative -t, shift should happen to the right side. Now compare this result and this result. Are they same? Yes. The case of combined operations of reflection and shifting, in whichever way we do, we get the same answer. The order is not important. But that is not the case with the combination of scaling and shifting. We have to be careful about the order there. We will see that in detail in subsequent examples. Plot -2 u of t minus 1. Here there are two operations involved. One is shifting operation, another is amplitude scaling. This operation is on dependent variable, this operation is on independent variable. Take the graph of u of t, shift it by 1 unit towards the right side to get the graph of u of t minus 1. Now multiply the amplitude of the signal by -2. The amplitude of this one is 1 multiplied by -2 will give you a signal like this. Here the amplitude is -2. So we get the signal -2 u of t minus 1. The next example, plot the signal r of -t plus 2. Here also there is a reflection operation and a shifting operation. R of t, which is the ramp signal, is the basic signal involved in this operation. Let us reflect this one to get r of -t. Now let us shift this r of -t by 2 units towards the right side. So the 0 point will be now at +2 point. From there onwards the same shape follows. So this is r of -t plus 2. You can follow the other order, that is from r of t, you can get r of t plus 2 first and reflect it. You can try it by yourself and see if you are ending up with the same result. Plot r of t into u of 2 minus t. Here there is a time shifting operation. U of 2 minus t can be considered as u of minus t plus 2. We know how to draw the graph. R of t is unit ramp signal. We have to multiply r of t with u of 2 minus t. Consider the graph of r of t, and for u of 2 minus t also. Now we have to perform the multiplication operation. We can see that from minus infinity to 0, r of t is equal to 0. So if you multiply 0 with any other amplitude of the second signal, the resulting product will have the amplitude as 0. Similarly, from t equal to +2 to infinity, second signal is having 0 amplitude. The product will be 0. That means the product is going to have value only between 0 to 2. Till 0, the product has got value 0 because of r of t. From 2 onwards, the product is 0 because of the second signal. Between 0 and t, the amplitude of the second signal is 1. So r of t multiplied by 1 till t equal to 2. That means r of t itself. So this part of r of t till 2 will be the product. The slope of r of t is unity. That is why it is called unit ramp function. So if this point is 2, amplitude should be equal to 2, so that slope is 1. So this signal is the plot of r of t into u of 2 minus t. The last problem of this video is plot 2u of t plus 2u t minus 2 minus 2u t minus 4. We can see that there are multiple operations involved, more than 2. Shifting operation is there, amplitude scaling is there, and addition is there, subtraction also is there. Let us draw the component signals. 2u of t, we can see that this amplitude is raised to 2. 2u t minus 2, we can see that this 2u of t is delayed by 2 units. And the third one is minus 2u t minus 4. The signal is delayed by 4 units and the amplitude has changed to minus 2. Let us add the two signals together, 2u of t and 2u of t minus 2. We have to do instant-wise addition. Is 0, both the signals are 0. The addition result also will be 0. From 0 to 2, second signal is 0. So only first signal amplitude will be there. Amplitude will be 2. From 2 onwards, first signal will be contributing an amplitude of 2. Second signal also will be contributing an amplitude of 2. So the combined amplitude will be 4. So the result will be like this. Now let us consider the third component, which is minus 2u of t minus 4. Adding this signal and this signal. Till t equal to 4, the pattern of the result will be like this itself, because here it is 0. From 4 onwards, this amplitude 4 will be subtracted by 2. So that the resulting signal will be like this. Till t equal to 4, it follows this signal. At 4, because of the presence of this component, amplitude comes down to 2 and stays there. This will be the final answer. 2u of t plus 2u of t minus 2 plus minus 2u of t minus 4. That completes the answer. With that, we have come to the end of this video. Thank you for watching.